Okay, so we have introduced several methods already, and you now already know how to solve two kinds of problems. You can solve optimization problems with no constraints, and also you can solve optimization problems with constraints. And when the problem is nonlinear, you can always linearize it. You can linearize all the functions to make it a completely linear problem. Then you can solve it by linear programming. When you find the solution, you can restart your linearization again at the new point. So you can repeat this process sequentially and hope you can get a solution. However, so far we haven't introduced any trick to check whether a solution is the optimal solution. Only the algorithm tells you, okay, this could be the solution because I could not find a better one. So you should stop. Every time when we have a convergence check, we check whether the algorithm can find a better one. If not, then stop. But it doesn't really guarantee true solution. So today we are introducing some kind of checking a tool that helps you to figure out whether the solution is optimal. Okay, so it's called the KKT condition. So KKT, okay, what is KKT? KKT stands for three people's name. Karosh, Kuhn, and Tucker. So basically 3 people. So KKT condition. Okay, if you Google KKT condition, you can find it. So we are introducing this KKT condition, and if a solution point satisfies KKT condition, it should be an optimal solution. Now, for a general constraint optimization, we usually have a formulation like this. Here, I'm just following my notes. So this time, I'm writing the equality constraints first. Okay, I better follow exactly my notes, otherwise there could be some inconsistency. So in my notes, I'm using J. So over here, we totally have n constraints, and some of them are equality constraints, the rest are inequality constraints. Okay? So we haven't introduced that yet. Hold on, let me find exactly where one line should be introduced. Hold on. Okay, there's a long derivation of one equation. I think that will occupy a lot of time. So I will just show you something by, let me see how I can show you. Maybe I show you by a graphical approach. So we want to prove a specific formula. So we're going to reduce this problem into a equality problem, equality constraint problem. So let's talk about a smaller problem first, and then we will come back. In this smaller problem where we have equality constraints only. Okay, let's talk about this one first. So in order to derive one equation that I'm going to talk about, we can try to formulate, draw a graph to indicate a specific example. So let's say there is a two-dimensional problem, and let's say I have the contour of the objective function, for example, something like this. Okay, and let's say this is the descent direction, which means the lowest point could be right here. This could be the lowest point of f. Okay. However, let's draw some constraints. In this case, if I have one constraint, for example, if I draw in a specific way, if I draw something like this, maybe a better one like this. Okay, so let's say this is h of x equals to 0. So let's say we only have one equality constraint, which means our solution has to be on top of this red curve. And basically, we're trying to find the position where your function value is the lowest on the trajectory of this red curve. By observation, you can tell the minimum will be somewhere right here. So this is actually the true optimal. Just do it like this. That's your x star. Okay? And that's stay on the green point and draw the contour of your f that has the same function value as the green point. If we do that, the contour will look like this. Right? So this is the contour level of f of x star on that dash blue curve. The function value equals to f of x star, and that's the lowest function value your solution reaches. If you pick up a different solution point on the red curve, a different one, the function value of that additional point will be higher than f of x star, right? So by observing the red curve and the dashed blue curve, you realize their gradient is parallel to each other. So the gradient usually is perpendicular to the function itself. And in our case, the gradient is actually going up. So let me show you what the gradient direction look like. Before I do that, let me move this curve because it's a little blocking my way. So let me redraw this. Okay, so the gradient of function f actually is over here, and it's perpendicular to the blue dash curve. This is actually gradient of f. Why is that the direction? Why not going inward? Because if you increase x a little bit, function value increases. That's why it's going to the upper right corner, not to the lower left, right? And your h, I didn't formulate h. I didn't mention whether h is having increasing values going upper right or going lower left. So the gradient of h could be either here or could be here. You just don't know because I haven't write down the mathematical formulation of this curve. So the upper right corner of h could be positive or it could be negative. It just turned out on the red trajectory it equals to 0. So it's like a either or. Either this one or the other one. So that would be the gradient of h. And the magnitude of gradient f and gradient h won't be the same. They are basically different functions. However, they are perpendicular to the function itself. Okay? So it turns out you can have a conclusion like this. Let me just put a number, some symbol alpha here. You can say that because they are parallel. Okay? They are parallel. Okay, now let's talk about a different condition where we have two constraints, if we have two constraints. So I can copy, you cannot, so I'm sorry. Let me just copy this whole thing and then paste it here. And I'm going to get rid of some of the unnecessary stuff because I'm going to make a different condition. Okay. Now, let's say I have a different function. So I'm going to call this h1. And a different function, let's say it's like this. Another a line. It's h2 of x equals to 0. Since now you have two functions and they must be 0, obviously the intersection is the solution. That's your x star. So in this particular case, if you try to draw the gradient of all three functions, let me show you. At that particular black point, which is our optimal solution, over here, if I try to draw the gradient, this blue vector is the gradient of f. And if I draw the gradient of h1, it could be somewhere here. Let me use red. This could be the gradient of h1. And let me use black. No, let me use green to represent the gradient of h2. So if you have more constraints, you realize they don't follow exactly what you mentioned earlier. They are not exactly parallel anymore. But you can say gradient f would be like a combination of these. Okay? With some weights. You can definitely find some coefficient in front of h, and the sum of them eventually equals to the gradient of f. It's doable. So when there's a equality constraint problem, and if the solution exists, you can always have an equation like this. The only problem is you just don't know the weighting coefficients. Okay, so in general, we can formulate something like this. In general, here we introduce lambda. Lambda, we call it Lagrangian multiplier. Lagrangian multiplier. Okay. Why didn't I use alpha? Because people would like to use lambda, and in my previous definition, alpha is on the right hand side of the equation, and for Lagrangian multiplier they like to write it on the left hand side. So to avoid confusion, I use different symbols, but they are basically weights. They are just weighting coefficients. Okay, so in general, we can have a equation like this. Okay, so this is what we have if we have a linear problem like this. Okay, a linear problem, the red one. We know at the solution, the gradient of the objective function equals to or summing the gradient of equality constraints multiplied by those lambdas. The entire total sum could be equals to 0. You can always find the equation like this. Okay. Now we are going to back to the general problem where we have our um, inequality constraints, G's. We already learned about slack variables. We can add slack variables to the G functions so they become equalities. So let's do that. Let's from the top, add slack variables to all the G functions, Gj's. Okay. So what we will have at the end is minimizing f of x subject to hi of x. I goes from 1 to m. G of j, Gj of x plus Sj squared equals to 0. J equals to n plus 1 to n. So this time when we add the slack variables, we square them. So we could be making sure the extra term right there is always positive. If Sj squared is positive, your Gj can only be 0 or negative. So this is an equivalent formulation compared with equivalent one to compare with the original one. Okay. Now we can actually combine all of it. We can combine all of them because they are now all equality constraints. We can formulate the gradient equation exactly like what we did earlier. So now we can just formulate this Lagrangian formulation. So we will have gradient f of x at the optimal plus a bunch of Lagrangian multipliers, lambda from 1 to m, and we would have gradient h of I, and then we could have a bunch of let me see. Just making sure. Should I use I or J? I think J is fine. J goes from n plus 1 to n. This time I'm using a different symbol. I'm using mu j, gradient of Gj x star. This could be 0, right? Okay, I'm gonna say sorry to you. I think I better use I instead of J. So I'm going to replace. I'm changing a color. I'm using I. Sorry. I think I better use I here. Okay. I made a mistake earlier. For the G's, I'm going to use I. Sorry, that's a mistake. From here, in this case, I should have I here. I think this would be better. They are I's. Yeah. I change them to I's. Okay? In this case, this should be I. Everything is I. Okay, everything is I here. Yes. Okay, everything is I. Now, do I need to, let me see. Where is my S? Because when we take the gradient, S disappear. S has nothing to do with X. S is S. So when we take gradient, actually, if we rewrite them, they are partial derivatives with respect to. This time I'm using J, the jth variable. So if you would like to write a more detailed information of your of this equation, this is actually partial. The gradient includes a bunch of partial derivatives, and this is the jth one. Okay, so this is the jth component in. Okay, so yeah, this is the j component in the above function, because the above function actually is a vector. There are how many of them? Depends on the size of x. How many was depend so j goes from, for example, 1 to, let me see, what's the number that I use? J I never define in this particular notes. So let's say j goes from 1 to n, capital N. So n is the dimension of x. Okay, so basically the gradient f has capital N of them. I'm basically doing partial derivative with respect to the jth one. And because your x has n of them, it's actually n equations. I'm just writing down the jth one. Now, it's gonna look like this. This is why I'm using J for X, not J for G, because it will be confusing. Right? So if you would like to write them down, this is how it look like. The whole equation look like this. The details are there. Okay, so this is very important equation. But when we do, when we take partial derivatives, we actually need to take partial derivatives with respect to all the variables. We also need to do partial derivatives with respect to the slack variables. We haven't done that yet. So to follow up, we also need to do partial derivatives with respect to select variables. Okay? What you will have at the end, I should be doing, remember we have SIs. So the select variables basically are SIs, where I goes from n plus 1 to capital N, right? N plus 1 to small n, not capital N, small n. We need to do partial derivatives with respect to those as well. If we do that, what we get at the end will be something like this. This time gi plus si squared over si. Okay? So to avoid confusion, actually we should use a different symbol because we have some sum of i's right here. It's not summing on the si right here. So to avoid confusion, we can always change index. Just change the character. So just in order to avoid confusion, we are changing them to j in this particular case. So it won't be confusing. You have to do it, otherwise your i's, those are summations of i's, will be confused with the si's. The i's here is not the same as your variables index. Okay? The i's are the indexes we had earlier for number of constraints, and for variables we use j. Okay, so why we have si, not sj earlier? Because for every g function we prepare one si. So that's the time we have same index. Because every g function we introduce one s variable. So they have the same index. However, when we do derivative, it will be too confusing if they are having the same index. That's why we need to use a different symbol to avoid that confusion. Now, is f a function of s? No. F has nothing to do with s. So this guy becomes 0. How about h? H has nothing to do with 0. How about g? G is g. G has nothing to do with 0. So this term becomes 0 as well. Only the s squared has relationship with the sj at the bottom. Okay? So it turns out I should not, okay, it's a little confusing. I should not change this one to j because this belongs to this belongs to the original function. This is because for example, we are focusing on the first g function, But when we do partial derivative, this could be the second variable. So there will be a term where you have the first function having a derivation with respect to the second variable. So these two indexes are different. Okay, so yeah, I made a mistake. So when will Si has something to do with Sj? Only when S equals to J. So this part is not 0 only when I equals to J. So only the jth term is not 0. So let's take a look at the jth term. So the jth term, so this is the jth term of this entire summation equals to the jth one. So basically, this is the jth one. The jth one only. The rest of them are 0. Okay, and if you reorganize this, at the end, it's gonna be like this. So basically, it's telling you mu j as, this should be j. Mu j as j equals to 0. And j goes from where j goes from n plus 1 to m. Okay? So, another important equation. Okay? Let me see if I can have this work properly. I'll give you some time to copy all this. Yeah, go ahead.
Yeah, I have one question.
Yeah.
So you mentioned J index is n plus 1 to up to n.
Why? You want to know why?
No, yes. And also for I also you mentioned n plus 1 is equal to n. So both indexes same. Because in new I you mentioned I is equal to n.
Okay, let's go back and see the original one. I from 1 to n are the indexes for equality constraints. From n plus 1 to n belongs to the inequality ones.
So both
So,
I is same.
There's the numbers. You can say this is a 1 to 100. And for example, it's 1 to 50. So you basically have 50 h's, h1 to h50. And this could be 51 to 100. So you have G51 to G100. Okay?
It should be the JKM and something, it should not be the I in the index. Because
Oh, you mean why can I just use a different symbol? But I can use the same symbol. The purpose of using the same symbol right here is to make sure at the end we could have more consistent form in this particular equation. Because I have an I here. I also need an I here. I want this one to be I. I can rewrite this as A or something, some other index. That's fine, as long as I'm properly defining it. So over here, I'm just clarifying, and I'm just precisely defining a summation from I equals to 1 to n. So over here, you have your h1 to hm. And over here you have g n plus 1 to g n. Okay, so that doesn't violate anything here. What I did was, I didn't use j for this particular case, because there will be too many symbols. I want j's for the variables. I could change this I to j. If that's the case, I may need to introduce k for x. That would be a lot of symbols. That's all. That's fine. But I just want the entire equations has I only and j's for the variables. Yeah. And that fits my notes. Okay, so over here, every time you introduce a select variable, it's specifically created for one particular g. So over there at the top, si goes with gi. So if you have g51, you have s51. So over here, you actually have s51 to s100. They are just 50 numbers. Okay, and over here in this particular equation, in general, earlier we are taking derivative with respect to all the x, but we forgot to take derivatives with respect to our select variables. So this equation has to be done repeatedly, but this time with respect to the j select variables. So over here, you can see at the bottom, I'm replacing all the variables for derivation derivatives from xj to sj. Okay, but when we replace the variables here, that doesn't mean we can replace anything on the top. It's the exact same equation on top. So what's confusing right here is that we originally have 50 variable functions right here. They are summing up together. So this goes from 51 to 100. So we have 50 terms. And this particular one could be S51. The next one is S52 and so on. And when we take derivatives, the whole equation, we are taking derivative with respect to one select variable only. So we are taking derivative with respect to a particular s, for example, S64. So the 64th one is right here. But all the terms on the top are still there. They are like 50 terms. And we are taking derivative with respect to that specific one, the 64th. And since all these terms has nothing to do with the specific one only, but that particular 64th one has something to do with it because it's the same variable. So only that term has something to do with Sj. That's why at the end, all these terms, the jth one won't be 0. So the non-zero ones is written here. The rest are just 0. Only that jth one is 0. Okay, when this term is j, this is j as well, because the I number goes from n plus 1 to n. Now we're talking about some particular one, the jth one, in this collection. The jth one ends up with non-zero values. So at the end, mu j times this, and it tells you it has to be 0. And it turns out we can derive some equation like this, mu j sj equals to 0. And this is mainly about j. And what does j ranges from? J ranges from n plus 1 to n. Basically, the 51 to the 101. So now we have 50 of those equations. Mu j times sj equals 0. So basically, mu 51 times s51 equals 0. Mu 52 times s52 equals 0. Basically, yeah, basically something like that. Okay. So let me try to get back to here and see if that works. and then full screen right here. Okay. So very good. We now have two important equations. What else? Okay. Okay, so there's even when we derive this, we need to make sure it guarantees optimality and feasibility. So we are not sure, we need to check. So we want to check optimality and feasibility. So basically just see whether the equation guarantees those. Okay, so now let's talk about feasibility first. There are ways to, in the derivation, they try something to figure out, to prove what we had earlier guarantees feasibility. So what happened was, let's say at the neighborhood of your optimal solution, just somewhere really close by. If you have introduced a small, very small perturbation. Perturbation is like a small change. Perturbation to x. It's like changing your optimal a little bit. Okay? And we want this perturbation to be a feasible one. So let me add one word, a small feasible perturbation. So it's like if I have a graph, the earlier example, for example, this is my descent direction, and for example, this is my constraint, okay, and supposedly my solution is right here. So I'm having a small perturbation. So basically I move this point to somewhere just by a little, and let's call this movement D. Okay, a small perturbation. Okay? But when we do that, sorry, not exactly the same as earlier. Let me say this is the inequality constraint. So for example, g of x smaller than 0. So over here is g smaller than 0. Here is g positive. So on the wall is fine. On the upper right corner of the wall is fine. On the left lower side of the function is not okay. So on the left lower corner, it's infeasible. So that's a better example. So now, if this D is a small perturbation, then what do? We can take a look at the gradient of all functions. So this is a gradient direction of your f. We already introduced earlier. So let me just move the d a little bit. This is my d. Okay, and from here you can tell this d movement cannot be having a angle like a more than 90 degree. This d movement, if I move toward the left lower corner, that movement will have a angle with the gradient f that is larger than 90 degree. Right? So what I'm talking about is that this is your optimal solution. If this is the direction of your gradient, and if your small perturbation is this way, it's good. It will be feasible. But if your movement is right here, it will jump into an infeasible space. Not invisible. Sorry, this is about optimality, because this is not about the constraint. This is about the objective function. So if we move up going this way, the function value increases. So if I go this way, I will become less optimal. Right? Because if I go this way, my function value increases. But if I go this way, I will become more optimal, because my function value decreases. So is that right? Let me think about it. Is that right? This is the gradient direction. Dot product is positive. So I shouldn't explain in this way. Sorry. So since we already said we want to make sure this perturbation is feasible, so this perturbation can only have two kinds of. If I draw the tangent line right here, because it has to be feasible, then your perturbation can only be either tangent to the directed to the tangent, or it could be somewhere here. Because if it's going to the left lower corner, it's infeasible. So those are the two possible perturbations that remains feasible. Okay, so either the small perturbations here or here. In this case, this particular one is having an angle and it's less than 90 degree, right? Let's just call this theta. So basically theta could be smaller than or equals to 90 degree if we are having a small perturbation. So this actually is telling us the dot product of these two could either be positive or 0. Because when it's 90 degree, the dot product is 0. But if it's less than 90 degree, the dot product between the perturbation and the gradient direction is positive. Okay? Now, how about feasibility? The G function in this case, because when we go to the upper right corner, function value drops. So the gradient direction of the G has to be this way. This is the direction of the G function, G gradient. Because when we go left lower corner, G function value increases. So that's where our G gradient is. If that's the case, that's observed. That's the tangent again. And we said our perturbation can only be on the line or above. And now this time our G is going this way, right? So this is the angle. In this case, the angle, let me change the symbol. Let me call this phi. Phi. Phi is basically larger than or equals to 90 degree. If that's the case, the perturbation dot product with the G gradient can only be smaller than or equals to 0. Actually, I don't need a vector here. Gradient itself is a vector. Okay, that's what happened to the inequality constraints. Now, if we have equality constraints, that means I need a different graph. If this is my contour, descent direction, and if I have a constraint like this, h equals to 0, in this case, my optimal is here. Okay. If we zoom in and take a look at this position, and this is the like a tangent of that function equals to 0, when we have perturbation, we can only move along this boundary, because this is how we can have feasible perturbation. We can never jump to the left or the right hand side of that dashed line. If we jump out of that line, the perturbation won't be feasible anymore. So in this case, if I draw the gradient of h could be this way. It's always perpendicular. So this is always perpendicular. So we end up with d dot product gradient of h equals to 0. So we have 3 equations. These. The first one describes the optimality. And the other one, these two describes feasibility. Okay. So if you have a small perturbation near the optimal solution, they should satisfy. If that happens, then that particular point must be the optimal. Okay. Now we can try to do this kind of check to what we had earlier, what we had in the derivation. We are just pre-multiplying with this d perturbation. So let me call this equation 1. This is my equation 1. Okay, that is equation 1. And also over here I'm calling this guy equation 2. Okay, the two highlighted equations are 1 and 2. I'm going to apply this d vector dot product with 1 and 2 just to see what's going on. So now we do the d perturbation dot the equation 1. At the end we would have d dot product gradient f plus summation of I d vector dot product gradient of h I plus summation of I as well, but it ranges differently. So d, oh, I forget my multiplier, sorry. I should move here. The multiplier is important. Lambda I here. And move a little bit here. The mu I. Okay? So this is pre-multiplying the d perturbation. And we know at near the solution, we should have those three conditions highlighted by the yellow box. So if we are near the solution, this should be positive, and this should be negative, this should be 0. Okay? So if we want this equation to be valid all the time, the middle one is 0. The first one is positive. So on the right hand side, the mu I d dot gradient g has to be remain. This has to be negative, right? It has to be negative or 0. Otherwise, there's nothing to balance out the first term, which is positive or 0. And it turns out this particular term, mu I, therefore this has to be positive or 0. Otherwise, there could be a specific case that will make this equation incorrect. So the only general equation that makes all possible situations works is that mu I has to be 0 or positive. So this whole equation can be 0 all the time. So I'm going to call this equation 3. Okay. Now we are applying, now we are observing equation 2. Equation 2 was mu j s j equals to 0. Okay? Or this time, if you want to say mu I s I equals to 0, they are all the same. Because either you name it S or J, either you name it I or J, they ranges from, in this case, I or J ranges from n plus 1 to m. They are basically same function. You're just changing the name of the index. It doesn't matter. So since we know for each gi plus si squared equals to 0, since we know this, we can kind of discuss some all kinds of possible situations. Let's say in the condition of si that is not 0 and also si is 0, what will happen? If si is not 0, mu I has to be 0, because mu I times si has to be 0. Okay? Yeah. Yes. M. You're right. Sorry. Typo. Right? So the reasoning came from here. Too thick. Because if si is not 0, mu I has to be 0. Okay. How about in the case of si equals to 0? gi must be 0. Why? Because from here, when si is 0, g must be 0. Okay? So in all possible situations, either mu I is 0 or gi is 0. Okay? So we ends up with a conclusion. Mu I gi must be 0. That could be a general equation that covers all kinds of situations. That would be my fourth one. To sum up, all these four equations would be the so-called the KKT conditions. So let me write down the general to sum up. To sum up, for a general problem minimizing f of x subject to h of I of x equals to 0, I goes from 1 to m, g of I of x smaller than 0, I ranges from n plus 1 to n. For this general equation, when we want to check KKT condition, what we will do is KKT conditions. First, partial f partial xj plus summation I from the first one to the mth one, lambda I partial h ith one partial xj plus summation I goes from n plus 1 to n mu I partial gi partial xj has to be 0. So where j goes from the first one to the nth one depends on how many variables you have. Okay, second equation, mu I gi equals to 0, where I ranges from n plus 1 to n. The third condition, all the mu i's to be positive, same range, and that's the KKT conditions. How about the second one? Where is the second one? Second one goes mu j as j equals to 0. And over here, when we observe the second one, we convert that to the fourth condition, because we don't want to deal with slack variables. That's why we convert mu j as j equals to 0 into a new condition, which is mu I gi equals to 0. And that's why at the end we can only have all these without actually introducing slack variables. Okay, so how do we use it? If you find if you have an optimal optimization problem and you found the optimal solution, you can implement those to check whether that solution is optimal. If all three satisfies, it should be. So let's try to solve a problem. Let's try to solve a problem. A very simple problem. We can say x1 plus x2 equals to 10. And let's get so I have a line like that. I have contours like that. I need okay, so it would be x2 larger than x1, maybe 2 times x1 plus 3 maybe. There must be a solution for this problem. Is it active? Let me see. Yeah. So if I make a drawing of this, I can already now by graphic I can tell where the solution is. So the contour will look like this. Okay, and the this is x1 and x2. So x1 plus x2 equals to 10 looks like this. Okay, it's a equality constraint, right? And x2 greater than 2x1 plus 3 looks like this. For example, if this is 3, then it's gonna be like this. So this would be my g function. And because they're larger than, so the wall is like here. Okay, so my feasible space, in fact, is this line. That's my feasible space. I need to stay on H, but I need to be having G value to be positive of 0. So at the end, where is the position that I have the lowest function value? It's here. That's my optimal. So in order to figure out what that point is, I just need to solve the intersection for these two linear functions. So basically, x1 equals to 2x1, x2 equals to 10 minus x1 and equals to 2x1 plus 3. So at the end I have 3x1 and here is 7. x1 is 7 over 3. So x2 is 10 minus 7 over 3. So that's 23 over 3. So at the end, the optimal is 7 over 3, 23 over 3. Okay? It's based on a graphical approach, Let's check the KKT condition to see whether it's optimal or not. So I will have first equation, KKT first. So before I do that, I need to do the gradient f, gradient h, gradient g. So I will have 2x1, 20x2. Gradient h basically 1, 1, right? Gradient g, I need to rewrite g. So 2x1 minus x2 plus 3 smaller than 0. So gradient g is gonna be 2 and negative 1. Okay, those are what I need. So KKT tells me 2x1 20x2 plus some Lagrange multiplier times 1 1 plus some Lagrange multiplier and times 2 negative 1. This has to be 0. Okay, KKT condition 2 tells me mu times g is 2x1 minus x2 plus 3. This has to be 0. KKT condition 3 tells me mu has to be positive or 0. Okay, now I just plug in all my solutions. So if I plug in all my solutions, 2 times 7 over 3, 20 times 23 over 3, plus I can say this, plus 2 mu minus mu equals to 0. I actually ends up with mu plus lambda plus 2 mu equals to lambda minus mu equals to, this is 14 over 3, this is 460 over 3. So I can actually solve for mu, the bottom one minus the top one. Then I would have negative 3 mu. Oh, it's wrong. Why? Okay. Did I make a mistake? x2 equals to 10 minus x1. Yep. x2 right here. Yeah. Yeah. And 10. Yeah. Looks right. Okay, now let's continue to see. But now I have a negative mu. Bottom one minus the first one. I have 2 and negative 1. Mu has to be positive. If I have negative mu, that means it's wrong. What? Wait.
Hold on. Okay. When you change side from the 2 times 7.3 to the other side, so it will be negative. So minus 14 point divided by 3.
Where? I cannot see it.
2 times 7, if from the left side to the right side. 2 times 7 divided by 3. 2 times 7 divided by 3 is on the left side, right? That one is on the left side. The last line.
Last line here.
Yeah.
Oh.
Especially on the left.
Ah, okay, 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 okay.
Negative.
Oh, it scares me. Okay. Thank you. Scares me. Okay. You're right. So yes, good. Mu is positive. Okay. So that satisfy the third one is valid. Okay. And then we can plug in the when we plug in this equation, that means we assume it should be valid. So the first one is valid. Now we just need to check the second one. So now for the second one, I have 664 over 9 times 2 times 7 over 3 minus 23 over 3 plus 3. It has to be 0 because we stay on that particular equation. Right? So it's valid. That's your second KKT. So if your optimal solution satisfies all three, it should be the optimal. Let's try a different point to see if that additional point violates KKT condition. If a different point violates KKT, that means that different point is not optimal. So now let's try a different point. For example, 0, 0. Let's see if 0, 0 is optimal by this KKT condition. So in this case, the first equation becomes 0, 0. Actually, I can just copy this. Copy, paste. Okay. For 0, 0, the first KKT condition goes like this. Okay. And then we can solve for lambda and mu. In this case, mu equals to 0, lambda equals to 0. That's the only case. Right? So if mu is 0, that's fine. That satisfies the third. Okay? But how about second? Let's check second. Actually, it works. How come? How come it works? Why does it work? Yeah. I mean, if it's I can try any point, and supposedly all other points won't satisfy KKT condition. So I'm trying to figure out where I made a mistake. Somewhere must be wrong. Because in this case, mu and lambda are both 0. So everything becomes 0. Why does it work? Yeah? You found it? Why? You mean point? Yeah, you're right. But the KKT didn't ask us to check G, right? If we it doesn't satisfy H, it doesn't satisfy G. But the KKT condition didn't ask us to do that. It just asked us to check all these three. Or we need to check all of them. Yeah. If we check all of them, then sorry. The KKT want us to check the constraint as well. So when we do that, we will end up with that solution won't be optimal. So besides, I just checked my second page of the notes. Besides checking all these, you also need to satisfy the constraint, because it's an obvious rule, obvious criteria to be checked. Okay, and remember when we derive, we also use feasible perturbation. So all the rules were based on feasible perturbation. So you need to test it by a feasible point. So 0, 0 is not a feasible point. So let me try a different point that is feasible. So this particular point must be feasible. That point. That is 0 and 10. 0 and 10 is feasible. Now let's see if 0 and 10 is optimal. So instead of trying 0 and 0, I should try 0 and 10. Okay? I should try 0 and 10. In this case, I will get rid of these. It's a feasible point, but I'm not sure if it's a optimal point. So in this case, I will have something in the front, 0 and 20 times 10. Okay, so I will use the bottom one minus the first one, so I will have 200 minus 3 mu equals to 0. So mu is 200 over 3. So this one tells you the first condition valid. This one tells you the third one is valid. But how about the second one? 200 over 3 times 2 times x1 is 0 minus x2, that is 10, plus 3. Is it 0? It won't be 0, right? So it's not 0. If this one is not 0, then not valid. So in this case, this is not the optimal. Okay? You can write a program of this whenever you use computer to solve for optimization, and then use this to check whether it's truly optimal. It's like a final check. And numerically, remember when we use MATLAB to solve for optimal solutions, we sometimes reach to the optimal with small tolerance. We never reach to the true solution. When that happens, you need to allow small tolerance to KKT condition, because what you end up with may not truly be the solution, but very close. So when you numerically want to use KKT to check optimality and feasibility, you need to allow a little tolerance. Okay? That's the first part of today's lecture. We use a lot of time, sorry. there's a second part I want to introduce today, which is quadratic programming. But I guess I won't be able to finish it today because time is very limited. So I would try my best to introduce up to certain points, and if I cannot finish in time, I will use the next lecture to continue. Okay, so now we are moving on to a method called quadratic programming. So-called QP. Okay. So for quadratic programming, what we usually can handle is actually problems in certain forms. Quadratic programming doesn't handle all kinds of nonlinear programming. So what does quadratic programming handle? For a general problem, for general problems, let's say all of them are nonlinear. What quadratic programming can do is applying second order Taylor expansion, and for the constraints, both of them linearization, basically first order Taylor expansion. So at the end, you actually have a problem like this, where your constraint is second order. Your objective function is second order, but your constraints are linear. So quadratic programming is not that powerful. It only handles a problem like this. This is a quadratic function. Quadratic. And both of them are linear. Okay? So if we can have a problem like this, we can use quadratic programming to solve it. But how about general problems? Let's say F, G, and H, they are all nonlinear. What you can do? Later on, we can use sequential quadratic programming, just like sequential linear programming. Okay, so now we are not talking about the sequential approach. We're just focusing on quadratic programming. And quadratic programming handles the problems with quadratic objective function and linear constraints. Okay? So if that's the case, we can always have a problem like this. I will tell you what those are later on. What happened? H is our Hessian matrix. C is like a vector of coefficients for linear terms. How about where's the constant? We don't care about the constant. Because when you do optimization, if there's a constant, it doesn't affect the result. because we can ignore the constant. For the G and the H, we just write them in a matrix form, like A matrix dot product with our X minus a vector of the coefficients. That must be smaller than or equal to 0. For the equality constraints, N times X minus E vector. Okay? It's a general form. And very importantly, we still can only handle positive X. So this is important. Just like a linear programmer, we only handle positive X vector. Okay? Now, since we already introduced KKT conditions, let's implement KKT condition on, let's try KKT conditions on the formulation that we have so far. So let's go from KKT condition. And the first, the way we put F and G and H together, actually we call it Lagrangian. I mentioned it already. Lagrangian. Okay? Usually we use it, define it as L. L is actually F plus a vector of mu dot product with a vector of G plus, this time we are changing it into a vector of V dot product of H plus a vector of W dot product negative X. What's going on? Okay, so over here I'm rewriting this as negative X must be smaller than 0. So there are actually a bunch of inequality constraints. So the Lagrangian multiplier must be applied to negative X as well, and put those W times negative X terms into Lagrangian as well. Okay? This is the equation that we haven't applied derivative. We didn't do gradient yet. So what KKT tells us, the gradient Lagrangian must be 0. We will do that later. Okay? So, let's do that. The KKT condition said gradient of Lagrangian must be 0. So we will have gradient F plus mu dot gradient G plus V dot gradient H. Actually, yeah, that's fine. That's do I put a vector sign here? I think it's fine. Plus W dot gradient of negative X. Okay, this has to be 0, and then let's truly formulate those. Gradient of F actually ends up with Hagian times X plus C, and then gradient of G ends up with A. Sorry, one mistake. This time I'm not going to use mu. Instead of mu, I'm using u, small u. Sorry, small u. So we have UVW, not mu. So over here, the gradient of G gives me capital A and the coefficient u. Yes? Gradient of H gives me capital N, the product of V. The last one at the end, I will have minus w. Because x derivative ends up with 1, right? Okay, that's one equation. Okay, the other things we want to do is everything has to be feasible. So these two equations must be valid. Okay, and we want to keep the second one for later derivation. So the red box highlighted equations will be utilized later on. Okay, this is just for feasibility. But for the g function, it's a inequality constraint. We don't like it right now. We will handle it later on. Actually, we will handle it right now. In KKT condition, we want u. Another condition is u times g has to be 0 all the time, right? And also, we have w times negative x must be 0. That's from KKT condition. If I recall the numbers, this is KKT1, this is KKT1, and this is KKT2, right? So, and also KKT3 tell us the Lagrangian multipliers for inequality constraints has to be positive. That means W has to be positive. Okay, so we have these. I'm drawing a box, drawing a red box, and I'm drawing a red box for X as well. Okay, those are the conditions that will be needed later on. Okay. Since we have the second KKT, we haven't do anything yet. Let's handle this particular one. So mu g equals to 0. Let's try to do mu and then we plug in g. What is g? G is a dot x. Actually, a is a vector. A is a matrix. Minus b. This equals to 0. Okay? And this one tells us w dot x equals to 0. Okay, so this is KKT2 tell us. And this one is useful later on. I am drawing a box. But this one is not. U dot a dot x minus u dot b is not useful. So what are the terms that are useful? I'm trying to formulate some terms that are linear functions. How come this one is not linear? Because I have a vector times a matrix times a vector. It's actually forming a nonlinear. Is it? Yeah, it's forming. No. Oh yes, because that we have three terms now multiplying together. we are trying to find a bunch of equation that only has two terms multiplying with each other, so we can have a magic later on. So this particular one is not yet a useful equation so far. So we just keep it like that. Now, in order to handle the g function, because this one is not yet handled. If we observe earlier, we have in the original problem we have a g, and we need a ug equals to 0, and even we plug in, it's not an easier form. So we want to rewrite this whole thing in a different way. This time we are also introducing slack variables. So introduce slack variables. Okay, what we can do is so we use a capital S. It's a vector. This is our slack variables. And whenever we do that, we know slack variables has to be positive. When we do that, we realize the g function becomes a better form. It's having an equality sign, and also in this equation there's no 3 items multiplying with each other. So we will keep this one. This is something we like. And this one also. Now, there's something not yet described, which is let's observe what is not yet included into these red boxes. So let's do some kind of count. Starting from the beginning, whenever there's a symbol, we will highlight it. We have x. Okay, we have x. Here's x. Here's x. X. Okay? So x was properly defined. It should be positive. We have capital H. Okay, H here in the box. So H was utilized. We have C. C is here. Okay? In the second equation, g function, we have A, capital A. A was described somewhere here and here. We have X, already mentioned. Small b. Small b can be found here. Okay, that's all. Capital N. Capital N was mentioned in the Lagrangian. Okay. Small e. Small e could be capital N here, small e here. Okay. And we have 3 Lagrangian multipliers. Small u is mentioned here, here. And small v. Small v, I will highlight it. Small v is here. Okay? And small w. Small w here, here. Capital S here and here. So it seems like besides the matrices are coefficients, but the variables, let's focus on the variables and do this again. Sorry, I should separate the variables and coefficients. Let's only look at the variables that is being mentioned in this entire problem. So let me write down on the right hand side. First we have a variable x, right? There's a definition of x here. It's mentioned it has to be positive. There's a description about x. Now the second thing is actually u. U is our Lagrangian multiplier. U was described at the bottom here. It has to be positive. Another one is v, but there's no description of v. So v is the variable that we need to be taken care of later on, because there's no description about v. The next thing is w. We said w has to be, w has to be positive or 0. Okay? What else? We introduce slack variables. And we mentioned slack variables has to be positive. So we not yet talk about the Lagrangian multiplier for h, which is v. There's no limitation for v. And that's why here we are going to define something called y and z, such that v equals to y minus z, and v cannot be 0. Why does v cannot be 0? Because remember, when we first talk about very early, when we talk about this part, I forgot to emphasize it. When we talk about the balance, the summation equals to 0 for equality constraints, the Lagrangian multiplier cannot be 0. It's indicating the gradients of f equals to some ratio of the gradient of h. So that ratio cannot be 0. Otherwise, it's meaningless. Okay, so this is because the multiplier for equality constraints cannot be 0. Okay, that should be mentioned earlier. And we define y and z just to why do we do that? Because we want to say where y and z are both positive or 0. Because we want all the variables to be positive or 0. And we don't know how to define v, right? So we just say, okay, v is y minus z. And let y and z to be positive or 0. That doesn't mean v has to be 0 or positive or negative. It's a way to define v, but keeping the variables that we're going to use to be positive and or 0. So, because v could be positive or negative. We don't like variables that could be negative. That will not be useful later on. Because we are formulating a linear programming problem for quadratic programming. In linear programming, all the variables has to be positive. Okay. Now, when we introduce slack variables, remember earlier when we do that, we need to, in our Lagrangian formulation, when we do partial derivative, we will forget to take derivative with respect to our slack variables. And earlier we add that part of the derivation where we found mu s equals to 0, the red box number 2. So that is something I'm going to put right here, mu s equals to 0. And if mu over here is u s equals to 0. Okay? So I'm going to keep this one as well. This is from derivation of KKT. Now let's try to put everything together and see what we have. There's a lot of them. So first one, I'm gonna use a lot of copy and paste. First one, copy this one and paste it here. So it's like to sum up. Okay, this is the first one. But over here, we don't like a V. So whatever we pick up, I will draw a yellow line underneath, just to remind ourselves. Okay, that one was used. But over here we don't like V, so I'm going to replace it by y minus z. So over here, I'm moving this here, get rid of V, replace it by y minus z. Okay? Now the other box I'm going to use is gonna be this one. So that particular one, I will draw a yellow line underneath. Okay, that one's good. Next, I'm gonna pick up this particular one, the equality constraints. Paste it here. And I'm going to draw a yellow line over there. So that one's taken. Now, I'm taking this one. And draw a yellow line there. Finally, taking this one. Okay, and then draw a yellow line here. Okay, so for the rest, they are just indicating all the variables being considered, they are positive or 0. So let me write them down. We know x would be positive. Then we know what else? U. V now becomes y and z. And we know w is positive. We introduce slack variables, right? So x, u, v, w, v replaced by y, z as slack variables. They are all positive or 0. Okay, so from the general nonlinear problem, we now rewrite the whole thing into a bunch of linear equations. Okay? Here, these three are, let me show you where are the variables. These are variables. The red ones are variables. The non-highlighted ones are just coefficients. So from here you can tell they are truly linear functions. They are linear functions. But these two are still nonlinear because you have w times x. W and x are variables. U times s, they are nonlinear. So those two are still nonlinear, and we may need to do something with it later on. So let's focus on the linear equations, the first three, and then put them in a certain order. A very interesting order. Sorry, let me make the box larger. Okay, and then just make sure this should be fine. I will tell you what's going on. Okay, so let's check the first one. A times x plus 1 times s equals to b. That's exactly the second equation, right? A times x minus plus s equals to b. Okay, now let's check the second line. N times x equals to e. That's exactly the third equation. Nx equals to e. Right? Okay. Lastly, h times x plus a times u minus w plus n times y minus n times z equals to negative c. That's exactly the first equation. Okay? So we just successfully reformulate the three linear functions into this vector form. Okay, so let's call this guy capital B, call this guy capital X, call this guy capital D. Okay, so B dot capital X equals to D. This is a huge matrix, a vector of X, vector of D, and what else? All the X has to be positive of 0, and don't forget we need W dot X to be 0 and U dot S to be 0. Okay, so at the end we end up with something like this. Okay, So if you can find a bunch of variables, a bunch of x that satisfy this whole thing, this must be the optimal, because all these derive from KKT conditions. So the key is to find a bunch of variables that satisfies the whole thing. Okay, so one way to figure out one way to get all the possible solutions is to formulate a new problem. Okay, so the new problem goes like minimizing y1 plus y2 plus da da da. Y over here I'm giving a number, for example m. Okay, a bunch of them, and we define a vector capital Y equals to y1 to ym. Okay, subject to b x minus d plus y equals to 0. All the x and all the y has to be positive. Okay, so this is a linear problem. This linear problem can be solved by finding a set of x with all y's, let me call yi, are 0. So if you solve this linear problem by, for example, linear programming, and if you are able to minimize the summation of y, at the end all the y's are 0, right? So you must be able to end up with a bunch of x that satisfy this new problem where all the y's are 0 and all the x are just a bunch of x you don't know what they are. However, those x satisfy this equation, bx minus bx equals to d, and all the x are positive, right? So if that's the case, I will satisfy those two. It's one way to find possible vectors of x that satisfy those two. Okay? But it doesn't guarantee it's optimal. It's just a way to find a set of x that guarantees those two expressions. So all you need to do next is to check whether the other two equations are right or not. So once we have a bunch of x that satisfy those two, we will check those. Then we check those if those are satisfied. If not, we may need to have linearization again at the new point. So it's like a sequential approach. So if we use the new problem to get a set of solutions that satisfy the red conditions above, but not satisfying the yellow one, it's okay. We just it's like some solutions during the process is not yet the true solution. So we basically can, because everything came from linearization, and everything came from approximations. So what we can do next is try to make new approximations later on, and repeat all these again until we can find some solution that satisfy the new problem here and also satisfy the yellow part. So only when we can find solutions that satisfy all four, then we're sure that's a solution for quadratic programming. Okay? And since that requires a sequential approach, so many times it's called it's basically a sequential approach. Okay? But there is actually further derivations of sequential programming. But I think this is already enough to introduce quadratic programming. Because I had a master student earlier. His thesis was to write his own quadratic programming code. He tried, and it turns out the most tricky part was to handle the yellow condition, because even you solve the new problem at the bottom, you sometimes cannot reach the criteria of the yellow one. So it's really tricky. And my student, he spent months on working on the code. He checked a lot of literature. So there are different approaches to find that condition. So when he eventually figured out a way by checking the literature and then got the code done properly, he told me that, hey, he got the code right. He was able to find a solution. I told my advisor that I found a solution who was able to write the code to get this done. So my advisor told me, wow, that's really difficult, because that requires quite complex procedure. As you can see today, even we are able to derive a certain form that supposed to give you a set of x that satisfy the two equations in red. That doesn't guarantee the condition in yellow. So QP was quite complex. So in this particular part, I think I won't be writing codes for you guys, because even I do it, it may not reach optimal all the time. So later on, I will introduce how MATLAB do it. So in MATLAB, there's already a function. Actually, it's fmin_count. I think now your life is becoming better. Okay, time to quit. Yeah, actually that's my last slide. fmin_count. Okay.